So I've started the recording. So I want to talk today about two things. First of all, let me erase this whiteboard. Everybody can hear me, I assume? Okay. I'm going to share my screen here. Actually, let me do this. Okay. So, right. So let's see. I probably hopefully won't get through everything today because I didn't finish preparing everything. But what I will try to talk about, the main focus was to talk about this, the chalk engine crate, first and foremost, and some of the sort of foundational concepts that it's based on. In particular, there's a paper, hold on a second here. There's a paper called, let's see, there we go. So there's a paper, if I can change windows successfully, yes, called A New Formulation of Tabled Resolution with Delay, very catchy title, that kind of covers the concepts in a sort of conceptually elegant way, although it doesn't give you much information about how to put it into practice. And so one of my goals here is to, let me open up this is the paper. One of my goals is to kind of make some connections between the terminology in this paper and the kind of conceptual part and what the code itself actually does. And I think today, if all goes to plan, we'll cover the kind of easy part of how this works, which is to say the sort of positive part of finding answers. And we'll see a little bit what happens when there could be an infinite set of answers and so on. But I think we won't get to some of the weirder stuff when you start to introduce negative reasoning in particular. And so I think we'll cover that next time probably, because I would have to do a little more prep. But negative reasoning would be able to say something like, this would be the usual notation, but something like P is true if Q is not true. And when you start adding that, it gets a little more complicated. And we do actually want to be able to do that reasoning in a limited way, even though Rust doesn't have syntax like that. Which actually I think probably sidesteps a lot of the complicating parts, but our engine still theoretically handles the full generality. But we'll leave that for another time. So, hi, Tyler. So, let's see, where to start. Let me just, I'm going to bring my secret paper, which has a little bit of a plan. Right, so first I want to do a little terminology before anything else. Probably many of you have heard these terms, but it's always good to be sure we mean the same things. The first thing is, I think people usually call this a proposition. It's basically something that can be proven true. So like in Rust terms, this might be something like option of U32 is sized, but the notation that I'll be using today would be more like this. And in general, you would have something like, I don't know what to call this, the name of the proposition, and then some term, some type in here. In the full chalk desugaring, there's like a bunch of more complex things here, but we don't actually care for the purposes of chalk engine. We don't really care one way or the other. Just some kind of thing that can be proven, and they can be unified together. And then so then you have something called a query. And a query is usually written like this. Let's say this. And it means something it's basically the outside when you request answers. This is the thing you're looking for answers to. And answers would be like both a result of yes, meaning it is true, and then with a substitution for any variables. So in this case, there are no variables, this particular example, so there would be no substitution. This is just true or false. Like ask for answers. Answers have the form. But you might have a more general query like, in which case an answer might be yes if x is u32. And there might be other answers like yes if x is f32. And in fact, there's kind of an infinite series of answers here because you could have option of u32, like an option of option, and so on. So we'll come to that problem in a little bit and how we think about that. But that's the basic idea of a query. And so from the point of view of Chalk Engine, this part of the code that I'm going to cover today, at least, depends how far I get, we're basically just giving a series of answers. It's somebody else's problem to decide if they want more, how many they want, and so on. And the code kind of has like an iterator-like feeling, so you can stop at any time. And the last two things, not too relevant today, but usually helpful term. The goal is just a proposition. It's a little bit more general than this, but basically it's a proposition that you are trying to prove. So what are you trying to figure out? And a clause would be a proposition that you assume to be true. Any questions on that basic terminology? Okay. So, good. So let's see. Let's give an example. So here's a little program in Prolog/Rusty quasi syntax. This might have come from, so in the level that we're operating at here, we're really quite separated from Rust's notions of traits and impls. But of course, this might have come from, well, like this rule here. This rule says copy is true for U32, and of course it might have come from an impl like this, which the compiler sort of has implicitly. And this rule might have come from an impl like this, right? So it says, oops. Oh, well, so it says copy is true for option of t if copy is true for t. And there's kind of an implicit like for all t here that I'm not going to write because it's tedious. So this is our example program that we'll be working with for the most part. And the actually, I don't think we'll actually get to clone. So maybe we don't even need that. Just cut that out. Just look at copy, it's enough. So now we want to be able to take queries like, well, like a very simple query might be something like, let's do the simplest one. Is U32 copy? And we want to be able to get an answer out from this, right? And that's kind of the topic of today. How do we evaluate these queries? How do we come up with answers, however many there are, and so on? And that's exactly what this paper is kind of about. And it's based on this idea where the idea is that you have a solver, or the solver is kind of represented as a tree, sorry, a forest of trees. The state of the solver is represented as a forest of trees. And each of these trees is like some thing you're trying to prove in different ways you can prove it. And so the nodes in these trees have a particular form that's called, well, I'm calling it an X. In some of the papers, it's called an X clause for some reason. And I'm keeping up with that terminology. It's actually not called that in this particular paper. But the structure of this clause looks like, well, it's kind of the goal that you're trying to prove, and something called a delay set, and then something called the subgoals. So we're not going to get to the delay set today. This has to do with negative reasoning. But all of these things are propositions. So something might be like, you might imagine if we were trying to copy, not for this particular example, but let's come back to this example here. Solver concept. You might imagine if we were trying to figure out if option of U32 were copy, and somewhere along the line, we're going to wind up in a state kind of like this, which is saying, I can prove that option of U32 is copy if I can prove that copy of U32 is true. Okay, we'll come back to that. So these X clauses, there's like a forest of trees of X clauses, basically. And the idea is that we have this initial state. The initial state is going to take the query. So let's use our really simple query, copy of U32. The initial state is we're going to make a tree that looks like this. And now what's going on here? So first of all, there's an empty set of delay clauses here. That's what that pipe is. And right now, we'll always just see the pipe as an empty set. And then this is like the stuff we have yet to prove. So this root node is a little bit weird because we're basically saying it's always the same thing in the root node. We're saying, here's the thing we're trying to prove, and we haven't proven anything yet, so we'll put this here. Okay, and this is going to be a tree. So I'm actually going to represent it as a list. By the way, feel free to interrupt me and ask questions. I don't know if I'll notice the chat, though, if anybody posted anything. So we start out, the very first thing before anything happens, we create from our query one tree, and it has this root node. And then there are operations that we're going to do. There's a set of them, like 10 different operations, that add new nodes to trees or create new trees in the forest, which, when we're all done, kind of tells us all the answers. And the first operation is something called program clause resolution. And what it basically does is it says, if you have a tree that has exactly one, it's just a root. And the first thing you can do is consult your program and look for ways to prove the goal that you have to prove, this proposition. So if we go to our program, we have 3 ways we can prove that. We know that copy is true for U32. We know that it's true for F32. And we know that it's true for option of T as long as it's also true for T, for any T. Right? So we can try to apply those. And the way we apply them is we take the thing we're trying to prove here, this proposition, and we unify it with the sort of head of this clause here, right? And so sometimes that succeeds. That's great. In this case, it's only going to succeed once, which is with the copy of U32 at the top. So we're going to add a node then that says, okay, it's going to look kind of similar. It has the same goal, but what comes here would be all the conditions we have yet to prove based on this particular rule. Now, in this case, there are none, because this format basically means we can prove copy of U32 if we prove these subgoals, and there are none to prove. But we just end up with this. Okay, and this is a child. So now we have a tree. This is the root node in the tree. This is its child. We don't add any rules for like the copy of F32 rule, for example. We can't unify copy of U32 and copy of F32 because U32 and F32 are different types. And same for this rule. So we get exactly one child. And this child is kind of special because it has no goals left to prove. So we call that an answer. Basically, we just now proved that U32 is copy. And we proved it by saying, oh, well, there's a rule that says U32 is copy. So that's like an example that's so trivial, it's almost kind of confusing because it's so trivial. But this is the general shape of what we're going to do. Is we're going to start with these trees, we're going to add a bunch of nodes, and we're trying to get to the point where we have some node with nothing left to prove, and that's called an answer. And then we'll sometimes propagate those answers in between things. So let's do another example.
All right, one question.
Yeah, go for it.
So why do we have a forest of trees instead of just a single tree?
That's exactly what I'm going to show you now. Oh, actually, will I? Yes, I will. So the answer is that each tree corresponds to sort of some query that we're trying to prove, right? And in this case, the queries. Let me just work it out and I'll show you. But basically, as we encounter different kinds of predicates, or with different sets of variables, we're going to create new trees to represent them. But let's make an example. Suppose I were trying to prove. So it's example number 2. Suppose I were trying to prove copy of option U32. This is a little more complex. So again, we're going to follow the same procedure. We're going to start with a root node that is just sort of equal to itself. That's the thing we're trying to prove. And we're going to elaborate it by using the program clauses. And we go up here. We can't use this one because option and U32 are different types. We can't use this one because F32 and option are different types, but we can use this one. So when we unify, let me copy this rule. So we're going to apply the rule now. Okay, and when we try to unify option of U32 and option of T, we see we need a substitution that says, okay, we can do that if T is U32. Right, so we have some substitution that goes from this rule to the one we're trying to prove. And so when we do that, we apply that substitution and we wind up with a child that says copy of option U32 if. So we would take this T, but we apply the substitution, so we get copy of 32. Sorry, and this is a child. And this I'm going to take out because this is not actually part of the tree. This is just my notes. I'm going to put it in a comment here, like how we derived this part of the tree. So, yeah, okay, post. So, right, so this is the tree we had now. We started with the root node, we added a child, and this is not, unlike before, this child still has a list of goals, so it's not an answer yet. Right, and now we need to figure out what do we do, how do we prove that sub-goal, copy of U32? And the answer is this is where the forest comes in, because now we go looking for some tree where this is the label, this is the goal of that tree that it was trying to prove. And we don't have a tree like that yet, because this tree is trying to prove for options, and this one is asking for integers. That's a different question. So we would add another tree. And just like before, the root node of the tree is always kind of the same thing twice. And now we're actually, interestingly, this is the same tree we just did here, right? So we can do the same step of we'll apply the program clause rule. We'll end up with this. This is an answer. So this is also what they call the program clause resolution rule. Now, at this point, let me just pop over to the paper because
Nico, how come you made another tree when you, like, why not just make another subtree over on the line you had before? Like, why not just keep going down over here?
Because everything in the subtree has to be working towards this same, towards some instantiation of this goal. So this is working towards a different goal. Like when we produce the answers we get here are going to be our answers that prove that U32 is copy. But we're looking for in each tree, any answers we want in this particular tree should be answers that prove the option of 32.
So does that mean that every tree will only have up to one child if you're always changing goals?
No, we'll see that later. But there could be more than one way to prove a given thing. In this particular example, I guess there isn't. We'll see in the next example a case where that's true.
One question, Nick. So unification, is that just within a data type?
Unification, is it just within a data type?
32 for like what's the reason that F32 fails to unify?
Okay. So unification, it's basically the Rust type equality rules in this case, but in Prolog rules, normally it would just be basically the same string. It means like they're the same, right? So they're the same string. And U32 and F32 are not the same string, and there's no variables in it, so they're not equal.
Okay.
But so let me present. So Sunjay, to coming back to this question of like why are these different trees? Maybe it's helpful to say that, well, when we get to the actual code, there's actually a slightly different name for these trees that I was using that comes from some other text called tables. But the idea is basically each one corresponds to some goal that we were trying to prove, right? And they're interdependent with one another because proving one goal requires proving another. But when you create them this way, often these things can be really complicated and there might be cycles back and forth. And this allows you to kind of cache answers also between queries and so forth. So if you put everything, like these trees, this all seems very abstract, I guess, but it does correspond pretty closely to the code. And essentially, it's just how you organize the answers. So you're looking for answers for a particular sub goal that you may encounter many times. And so it's useful to have a tree for it so that all of those times that you encounter the same sub goal from different parts of the thing can refer back to that shared data structure.
So I guess the point is performance, right? Because you're memoizing the results of queries that you've already found, and creating a different tree allows you to do that.
It's not just performance. Like this is, another way to look at it, it also comes up when you have recursion to prevent infinite recursion. So I mentioned that like there's an infinite set of answers, and we'll see later that part of the having these trees allows us to produce that infinite set of answers correctly. So in contrast, I would have to in contrast, like a traditional Prolog solver doesn't have any trees in its state. It only has a stack, the things that it's trying to prove. And it can easily go into an infinite loop and never produce any answers. So I'll come back to that and maybe that'll help clarify it. But let me keep going with this because I want to show one more example and then we'll try it. So for now, just take it on faith that it's useful to have these trees and that they represent different questions like U32 or option U32. So at this point, we have now two trees. One of them references the other here. And in the second tree, we actually have an answer node, which has no work left to do. So there's another kind of step we can do now where we say, okay, we resolve this sub goal by using the answer here. So in this case, there's no variables, so it's a little maybe unclear, but we know that basically we know that this is true because we have this answer that says it's true, and that's what we were trying to prove. So we can remove that from the list of work to do, and we can have option U32 if nothing, right? Because we use that answer to remove this, and now this is another answer. And so now indeed we know that option of U32 is also copied. And at this point, there's nothing left we can do on this tree because all of the nodes in the tree have answers as children, so we're done.
So that gets replaced in the tree, right? It's not on another node.
What's that?
The answer it removes the part of the node, or does it create a new node?
It's a new node conceptually, at least. In the actual code, like some of these, this is sort of the mathematical formulation, and nothing ever gets removed; it just gets added. But the reason for that is you'll see later that it is possible. Well, let me just give you the next example. It's possible to have many children. So far, we've only had one children of any given node, but it's possible to have more than one. So let's do the next example. So this one would say, here I'm saying, give me, this x is meant to be a variable. And we're saying, give me all, yeah, I'll do it like this. Give me all the x, all the types x, such that copy of option of x, or such that option of x is copy, right? So the correct list of answers is, as we said earlier, it's kind of infinite. It could be x could be u32, x could be f32, x could be option of u32, x could be option of u32, and because all of these types are things for which they are like an option of this is copied. Does that make sense so far? No? Or
Yeah, it does.
Okay. Okay. So how do we do this one? So let's walk it through. So we'll make a tree. We'll say, okay, copy option of u32 if copy of, sorry, not u32, copy of option of x, if copy of option x. And this is the first time that we've actually had a variable in our tree nodes. And I'm being a little hand wavy here about how we know it's a variable. Like basically, if it's a single capital letter is my convention right now. But in the code, of course, we're more explicit about this. But the meaning for this is find, when you have variables, the meaning is always, an answer for this will have to be a specific value, will include values for all the variables. Unless it, or if it, a partial substitution, values for all the variables that matter, basically. So if option were always copied no matter what x is, you wouldn't necessarily have to include a value for x. But that's not true in this case. All right, and so now we go up and we, or I'm going to call this, I'm going to do one other thing, and this is relevant. So I renamed x to a, right? And in my query I wrote x, but here I'm writing a. And that's both because, of course, the names of the variables doesn't matter as long as they're within one thing. But also this corresponds to what we call canonicalization in Chalk. So basically, one of the steps in Chalk when you try to create a table or when you create a tree in the forest is you canonicalize the names of all the variables so that they start, in this case I'm starting from A and going B, C, D, like in the order in which they appear. And that way, if you had multiple queries that are all kind of variations of this, you'll end up at the same tree. But one easy way to do that is just to always have consistent naming. So copy of option A. So this is our state. And if we go back to our rules, we can't apply U32. We're going to do the same thing as we did before. And there's only going to be one program clause we can apply to make the child, which is, we can apply this one, the one we have the same as here. But this time, the variable t winds up getting mapped basically to a, right? Because the t from that clause, because that's the thing. We still don't know exactly what child we're proving for. And so now we have to prove, the sub-goal here is now copy a, which is different from copy u32 because it has a variable in it. So we'll make a table for that, like this. Sorry, yeah, we'll make a tree, I guess. Or a table. And now we have to find answers for that. And here we get a little more interesting than some of our other cases because there's actually, all of these rules could unify now because we have a type variable. So we can make 3 children. We can make copy of U32. We can make copy of F32. And we can make copy of option A if copy of A. And I want to point out a few things. So first of all, coming back to Sunjay's question, you see that this part, the left part, these are all versions of the root node, but they have some things partially specified. So if we look at this, like when we go down this path to proving that root node, we actually have a value for A now. I'm going to call this B because it doesn't matter, just to make it a little less confusing. And here we have a value for A, which is F32. And here we have a partial value. We know that it's an option, but we don't know what it's an option of yet. So as we go, as we go down a tree, we always stay with something that can be unified with this original goal we were trying to prove, but it gets more and more specific.
Question.
Mm-hmm.
So we also store some kind of substitution table which says that like A is U32, like when we produce a new subtree.
Mm-hmm.
So like,
Right.
is this information like really stored, and like probably it should like be mentioned in the paper doc just to see it?
Yeah, I'm going to come to map to the code, but what we actually do here, it's a good question. So in the actual code, if I recall, I think we only store the values for these. We store two things. In the table, for each tree, we keep this root goal that we originally had. And then for each child within the tree, each node within the tree, we store the values for these variables. So we wouldn't actually kind of repeat all the information. We would just kind of keep like A is U32 here, saying in this path, that's what it is. In this formulation that comes from the paper, you can sort of reproduce that by unifying the two of them and figuring out what the substitution is that makes them unify.
Yeah, makes sense.
Okay. So, right, so now we have 3 children here, and interestingly, 2 of them are answers. And this one is not an answer node. However, it is an instance of something which we hadn't seen before, which is a cycle, which kind of gets back to some of the questions Sunjay was asking, I think. But so this sub-goal here, copy B, we already have a table for it, and it's actually ourself, right? So what we can do is we can add answers to this node by taking them from other parts of this same tree. So we can say, well, if B, for example, were U32, that would be one sort of child we could add, and we could add another one for the case of F32. But now, as we do this, we're creating more answers, right? And this is where you get that infinite set, because we could go ahead and add one like this. Which comes from here, right? And so you can see that we'll never actually, if we keep repeating this process, we'll never really reach a fixed point. We'll just keep growing the tree infinitely. But we always, at any point, we have a kind of partial set of answers. These are the answers we found so far.
And do we actually detect this cycle? Like, and if we detect this cycle, how do we do it? By using canonicalization?
Yes, we detect this cycle, and yes, through canonicalization.
So in the actual code, there would be A and not B in the
yeah. You could think of it as we canonicalize this. In order to find a tree for this, we canonicalize it. So copy B is canonicalized to copy of A, which has a tree. It's not a matter of thinking of it that way. That's actually literally what happens. And then since it has the tree, we can go look for answers within the tree. The way that we handle this in the code, I'm gonna start mapping now to the more concrete code, but it's basically the goal is usually not to run till a fixed point. Part of the reason I showed it this way of like building up and applying these steps one by one is that the goal is to iteratively produce answers and decide if it makes sense to keep going. So in the case of, if we were actually asking this query in the Rust compiler, we know that we kind of don't want to guess the value for X. So if for some reason we haven't figured out what X is yet, as soon as we get 2 different answers that aren't compatible with one another, like if we get U32 and F32, we can just kind of stop. We don't have to keep going because there's nothing useful for us yet. Like we're not going to be able, X is not uniquely determined, so So we should just stop searching for answers and see if other parts of the program constrain X. That might be jumping up too far a level, but basically what I'm saying is, yeah, there is an infinite set of answers, but that doesn't mean we have to produce it. Right? That's kind of up on our caller's job to try to not keep asking for more answers when they're not that useful. But this is one of the challenges, and we have also some safeguards in the engine that I don't plan to get to today that basically stop it from producing. If things are getting too big and it seems like we're producing too many answers, they start to just say, to just produce uncertain values. They will stop it so that it always eventually stops. So hopefully those safeguards don't kick in because they force us to produce approximate results. Which today in the Rust compiler corresponds to an overflow. But all right. So this is the way that the paper looks at things. I failed to reference back, although I meant to. I'm just going to show you real fast, in case you are curious to read the paper. This is the way they notate things. So I mentioned there's these trees. This is an example of the tree. Here's the root node. Here are the children and their children. And we didn't get to failure, but sometimes you have failures where that basically means this was not provable. This was false. So children can either yield an answer. Eventually, a child should either yield an answer or fail. Sort of. And they have basically, here's the set of things which say, these are the operations. I've mentioned these three so far. So like program clause resolution, positive return, new subgoal. These are the things where we say, taking the tree and what, this is like the state machine transition rules. Take the tree. If these conditions apply, we can add a new node to the tree. This is saying we can take a program clause. This is saying we can propagate an answer from one tree to another. And this is saying we can create a new tree. All these other things have to do with negative reasoning, which we're not going to get to yet. So those are the basic three operations. Okay. And now let's look a little bit at the code. Oops, not new code. Code. So let's see if I remembered all the things I meant to talk about. It looks like I did. So let me try to show you how this stuff, this kind of abstract stuff I've been talking about is represented in the code itself. First of all, the forest of trees is in a type creatively called the forest. And it has a list of trees, which I call tables. I confess this is a little incongruous, and a stack. The stack is, when we're not actively doing anything, the stack is empty, but Alexi, the stack, we'll see it later, that's how we detect cycles, per your question. And we can just ignore the stack for now. So the list of tables, the tables is just a vector. We map, here we have, so this big type, so what's going on here, first of all, let me step back. This C in the Chalk engine itself is very generic. It just thinks about logical things and doesn't know anything about Rust and so on. And so this C supplies like all the concrete types for how do you represent a proposition? How do you represent a type? That kind of stuff. So in this case, this U canonical goal environment, this is saying, basically here we're mapping from the canonical goal that we're trying to prove to an index of an actual table. So if we come back up here, the canonical goal would be like one of these, or here a copy of option A, something like that. And that's how we detect if we already have a table for that goal. We can find the index. Otherwise, we can. Well, there's even an operation probably somewhere here. I don't know. Anyway, and then there's just a vector of tables. And the table is tables here. And this starts to look a little bit different than the mathematical structure. So but there's definitely a mapping between them, but it's different. Let me explain it. So we got two main things. The first is a list of, okay, so the first is a list of answers, and the second is a list of strands. And what that corresponds to in the mathematical table is basically, for any given, we don't keep all the intermediate nodes in the tree because it's kind of unnecessary. So we keep the leaves, basically, all the leaves at any point. And we keep, well, I guess you could say we keep leaves and we keep intermediate nodes where there might yet be more children, right? And so the leaves are either an answer, in which case we're going to put it in that answer vec, one where there's no more subgoals left, or what we call a strand, which is like a thread, like work to do. And that's where there are still subgoals remaining. And so when we have some intermediate node like this one, this one was a case where we actually were able to produce 3 different subchildren. Right? So what we would do is we would take that one, this would be before we actually produce these 3 subchildren, this would be a strand. We would find the rules and we would produce 3 more strands that need to be processed, one for each rule that we could apply, right? And then some of those strands would get converted to answers if there's no more rules left, maybe all of them. That's the basic idea. So the strands are work left to do, and the answers are answers we've already found. And what we do is we give these answers in order, basically the order in which we found them, the 0th answer, the first answer, and so on. And that, we'll see that in a second, why we want that. So now that's kind of the steady state. At any given point, you have a list of a forest of trees, which we call tables. For each table, it's a table of answers. We have a set of answers we found so far, and we have a set of things we could do that might produce more answers.
So the strands are kind of like the leaves of the trees?
Yeah, I think it's safe to think. It's like leaves with active subgoals, with non-empty lists of subgoals.
Do you know why they're called strands?
I called them strands because I think of them as threads. That's not a term from any paper or anything. So I think of it as a thread because what we're going to do later, I'm going to talk a little bit about like the scheduling aspect of this sort of the search order. But the idea is you're incrementally growing this tree, right? And it kind of matters the order in which we choose to evaluate, how we choose to walk the tree. So the strands are like a given direction we can go, and like any thread scheduler, we want to kind of make sure that all those strands have time to, or have some share of the total time that we spend working. Does that make sense? So you can think of it like if you had to solve, if all the tree sort of exists in your mind, in potential space, and you have to explore it, the strand is like a particular path that you're taking down this tree. Maybe it should be called path. I don't know. It's clear that we could go over these terms and try to unify them, and that would be interesting. So, right. An actual strand, let's see, is represented here. And there's actually 2 types here, but let's just ignore the canonical strand for a second. So a strand consists of an X clause, which is the term for this funny notation here of like the 3 parts, basically, the thing we're trying to prove, the delayed things, which we didn't do, and the subgoals. We'll see it in a second. And it consists then of a selected subgoal, which is basically what part the strand is working on now, if any. We'll come back to that. Wait, I'm going to add a link to that. Oh, let me talk two more things to say about strands. So the strand is basically an X clause. There's a little bit of extra state called the selected subgoal, but it's basically with a label from one of those nodes in the tree. And an X clause. Oh, I wanted to talk about the canonical strand. No, I don't actually. The canonical strand is just a strand that's not active, that's been canonicalized. the details of that have to do with how Rust-C's inference tables work, like why we need that. Otherwise, you could just keep strands as they were. In fact, earlier versions didn't have a notion of canonical string. So TLDR doesn't really matter, but we'll come back to it later. This is the way we represent an X clause. So MacLad, per your question, we have, this is the list of things we have yet to prove, the sub-goals. This is the list of delayed literals that are needed for negative reasoning that we haven't used yet. And this is the way we represent that, the thing we're trying to prove. And you see it's just a substitution. So we don't repeat the information that's always the same for everything within the table. So this would be like the A equals U32 and so on. And for any act, that makes sense? Okay. So let's actually walk a little bit through this and see how this works. So these are the pieces. And what happens, there's a basic operation that, oh, actually, I think I have some links copied. Let's copy these over. The way that, what happens in the actual solver, like the outermost interface, before I get to this, sort of the solver interface you can do is you can say, here is a goal. Here's a canonical goal, G. So for example, this might be, in terms of our stuff we've been doing, this is basically something like that. And you can say, give me answer n from that goal. Right, and usually you would start at 0, and then you would go to 1. So you can keep asking for more answers if you like. Actually, I think you actually get, it depends on where you draw the line. I think the fundamental interface is like a slightly abstracted is you get back an iterator of answers. But internally, the iterator is going to ask for answer n from goal G. And let me show you what I mean by ask. I mean, where is it? Okay, well, this is where you get the iterator. So you say, iter over the answers for some goal, and it gives you back a stream of answers, right? And internally, what that's going to do is keep a counter, and it's going to call this method called ensure answer recursively. So what this tries to do is it says, given some goal that we're trying to prove, so the table for some goal, find the answer number n. And the reason I call it ensure is that this state persists between queries. So it might be that we already found a 0th answer for that particular, or an nth answer for that particular goal, in which case this is just going to return immediately. But if we haven't found that answer, then it's going to go do the work to try to find it. So you can see that here's the actual logic. The first thing it does is it loads the table which corresponds to the goal, and it checks if there's an answer already, and if so, it just returns it. All done. Otherwise, it checks for cycles on the stack. Let's just ignore that for a second. Otherwise, it calls this pursue. So pursue next strand. So if we visualize it, how this might work, if you had, like, let's say the first thing you did was you asked for a copy of U32, you might make a table which corresponds to, where was the case where we had 2 links? No, let's go through the examples one by one. If the first thing we asked was for copy of U32, we would make a table for copy of U32, and it would come up with an answer 0, which is just like yes with an empty substitution, because there's no variables. And then if we later asked for copy of option U32, it would create a table for that, which would internally ask for the 0th answer from this table, which would get it cached back already. And and thus it would eventually grow another answer here, and so on. Right? And then if we asked for a copy of option of x, I think is the way I did it, or however it was. Or if we asked for copy of x, well, anyway, as you ask for more tables, they may reference prior tables. Well, there is actually, yeah, we'll leave it at that.
So how do we ask for a table copy of option U32 first? It would have created the other table for copy of U32?
Yeah, so what do I mean by ask? What I mean by ask is that you invoke, like at the outermost level, it means you tell the forest to iterate over the answers for that goal, right? But internally, there's, it might ask in some sense as well by calling ensure answer recursively. So I guess there are multiple people who can be asking, but does that make sense? Maybe not.
Yeah, that makes sense.
Okay. So let's see. So let's look. What does this actually do? So if I mentioned that it'll return a cached answer if one exists. Otherwise, it'll go to compute one. Pursue next strand itself isn't that interesting. Its basic job is to grab. It goes to the table. It pops the strand from that list of strands that are pending, instantiates it, which has to do with how Rusty manages memory. But so most of this, like all this logic here, I'll come back to it in a second. But this is basically saying process that strand that I popped, and then it propagates the answer. And so the process that strand that I popped basically winds up going through. I don't want to go into the details of this. I'll come back to it in a second. But suffice to say that it calls this method sooner or later called pursue strand. Right. And so this point is when you say, okay, let's come back to our reasoning. In terms of this logic, we've basically now descended into some subtree, and we're trying to take the next step based on its current state. So we have the X clause. It has a list of pending subgoals that may or may not be empty, and we want to examine it and figure out what to do. So we'll go and say, okay, if no subgoal has been selected, so if we come back to, let's actually work through an example. Let's say we were trying to do, what was the one here? Copy of A. We'll do this. Suppose we were asking this query. We would create the table for copy of A, and we would, I didn't mention this, but when we create a table for a given goal, if you remember, whenever we did things, there was this, the root node was kind of special, and then the immediate children of the root node, they all came from the program clauses that we had from our program here, right? And so those two steps are kind of special and different because that's where you actually load from the program. So what we do is we do that immediately. When we create the table, we also populate it with all of the results from the program clauses. We don't have to do it that way, but it's convenient to do it all at once. And actually, Detrumi, I don't know your real name, sorry, I forgot, Lucas, I think. In any case, that callback you were writing, that's exactly what does this work, in case you're curious. Or it's exactly where we get the list of things from. So we would be in a state like so, where we have a table with 3 strands. As soon as we create the table, we would populate it with 3 strands, but no answers. So maybe I'll write answers, strands. Also, I should not have this be a text area, but that's good. And so now what we would do is we would pop one of these strands from the list of pending strands. Let's say it's this one, and make it sort of the like active strand, right? And we would then try to process it. And in this case, it's a very simple strand because there's no answers. So what we would say is, first thing we try to do is find some subgoal within the strand to focus on. Right now, there are no sub-goals at all. So we call this function pursue answer, which basically means I'm pursuing this strand to see if I release for an answer, and I found an answer. There's a lot of logic here, but that's mostly around negative reasoning. What's going to happen in this case is because there's nothing left to do, we'll just call this an answer, right? So we would add then a equals u32 to our list of answers, and we're done. And we would return back saying, here's answer 0. You asked for it. Now, if they came and asked for answer 1, we would pop off the next strand and process that, which would get us a equals f32. And now if they ask for answer 2, this is where things get a little more interesting, because when we pop this strand, it actually has subgoals. So we would select this subgoal to work on. And I'm going to denote that. Well, let's see. So we would make this the active strand, like so. We would sort of mark this one as the active subgoal. And what that means is we're going to remember our answer index, which starts out as 0. And we're going to go ask the table for this subgoal if it has an answer 0, which in this case is the same table we started with. So we have a cycle now where we're asking ourselves, what is answer 0? But it turns out we have an answer for that. Like we don't actually, because there's a cached answer, there is no cycle. We don't have to worry about the cycle. We can supply the answer. So we'll get back the answer a equals u32, and we will then apply that to our strand and make a new strand. This is the key point. Make a new strand of work, I'll put it here, which is like and then we have still our old strand, which we can kind of put back for later, because it may yet have more answers to give us. So we can put it back, and that's our current state now in some sense. We pursued this strand, and what it did was it gave rise to another chain of reasoning by using a previous answer. And if we keep doing this, if we pursue this one, we'll get option of u32 and so on, and we'll just keep finding more answers as people ask for them. And this will keep growing. Right? So I realized I was running short of time, so I kind of ran through this last part really fast. But did that make sense so far? Any questions on that last part? Because if not, I think what we'll probably do is stop here, and I'll come back and revisit this last part in more detail the next time we do this.
Ask you, Nico, if you'd be able to talk about this on Wednesday at the meetup or not.
Which meetup?
Like the Wednesday's Boston Rust meetup.
Ah, the Boston Rust meetup. Plausibly, yeah.
I just want to ask you some questions about it then.
Oh, yes, we could definitely talk sort of just one-on-one. I'm not sure if I'd want to present on it without a lot more prep. But
All right, thanks, Nico.
all right. Thanks, everybody. See you next time.